Hello, everybody. So, Craig Van Covering is continuing with his second talk on extremal Kähler metrics.
Okay, so part of my talk is in notes and part is in slides. So okay, so the talk is going to be about extremal Kähler metrics, and so the definition, in case you weren't here last week, is a Kähler metric, so that the Hamiltonian vector field of the scalar curvature, so that's called the extremal vector field. So this is in as a real vector field. The definition, extremal Kähler, is the Kähler metric, so that this Hamiltonian vector field of the scalar curvature preserves the complex structure. And because it automatically preserves this symplectic form, this is equivalent to the vector field being Killing. So most of the literature uses complex notation. And so soon I'll switch to the symplectic picture because like the project that I've been working on is involves like the symplectic picture of these metrics. But usually you're dealing with the set of metrics in the Kähler metric. You have a given Kähler class, and then it's easy to parameterize the set of metrics in the Kähler class in terms of potentials. So this follows from the d bar lemma using the Hodge decomposition theorem. And so then this is a convex set of potentials. So and the end of last talk, I mentioned like a paper by Matbucci, an old paper by Matbucci, where he defines a weak Riemannian structure on this set. And so then a lot of the recent work has been, so that's just a weak Riemannian structure on this infinite dimensional manifold. Well, I guess sometimes you consider this to be the set of all potentials. Here's the metric. But you can define, it has a weak Riemannian structure, and because it's only a weak Riemannian structure, you're not able to get geodesics to exist normally and such things. So a lot of the recent research has been to consider a much weakened regularity, like this regularity, and when you can prove that there exists geodesics, and then you consider the geometry of this space as a Riemannian space. So we'll be doing something different on this, so that's just a remark. But another basic thing is that for these metrics, there's a functional on this space where I guess maybe this is normally the set of potentials. Here I wrote it as the metrics. But it's the squared the L2 norm of the scalar curvature over each metric in this space. So I just like normalized it by the subtracting the average of the scalar curvature, which only depends on the Kähler class. But that's not really necessary. And so then it turns out to be a basic part of the theory, and this goes back to Calabi's original papers, is that if you take the Euler-Lagrange equations of this functional, you get this equation where I'm using like here complex notation. So del hash is the given here. So this is the you take the complex gradient of this function, the scalar curvature, and you take the 1, 0 part of it. And then this is del bar acting on vector fields of type 1, 0. And so the vanishing of so then this is it's a joint. So this is a fourth order operator. But then this being 0 is just saying that that this gradient is holomorphic. So the extremal vector field will be the I guess like 2 times the imaginary component of this vector field. And so that gives like the other definition of extremal Kähler metrics, that they're critical points of the Calabi functional. And so I guess I mentioned last time that extremal Kähler metric. So it's just some slight generalization of a constant scalar curvature Kähler metric. And extremal Kähler metric is constant scalar curvature if and only if the Futaki invariant vanishes. So this is actually like just like a 2-line proof in terms of the Futaki invariant. So some other remarks that motivate these metrics. So I mentioned that they don't always exist. So so the Futaki invariant just obstructs constant scalar curvature metrics, so that's not an obstruction, but there are stability obstructions to extremal Kähler metrics, as there are for constant scalar curvature metrics. But on the positive side, it is known that these metrics are unique. In the in the space of metrics in a fixed Kähler class. If there exists an extremal metric, then well, to be precise, it's unique up to the isometry. So if you notice that if you take a holomorphic automorphism will act on this space, and the orbits will be of the holomorphic automorphism group will be isometric Kähler metrics, because they fix the complex structure but they're taking the Kähler form to another Kähler form, but they're isometric Riemannian metrics. That gives an isometry. So uniqueness means they're unique up to isometry in the Kähler class. And so it's well known, it's been proved, can complete generality for extremal Kähler metrics, that if you have two extremal Kähler metrics in the same Kähler class, with the same Kähler class, then there exists a holomorphic isometry, sorry, a holomorphic automorphism of the underlying complex manifold, which takes one to the other. So this was proved for the Kähler-Einstein case, so in 1985 by Bandu and Mabuchi. There's a paper by Chushan Chen and Gang Qian in 2008 proving this for constant scalar curve. I think just constant scalar curvature Kähler metrics. I'm not sure if it does extremal also, but I've talked to experts and nobody seems to understand this paper. It's like really long and esoteric, using holomorphic disks. But there's a like modern proof using pluripotential theory, which is just like 25 pages by Berman and Bernsen, that proves it in complete generality. And this is also interesting in that I haven't defined it, but there's an energy on the space of, there's an energy on the space of Kähler metrics in the Kähler class in this space called the K energy, or sometimes called the Mabuchi energy. And it's basically a Kemp-Ness functional on this space of metrics. And so the proof in this paper, which is interesting, is that the K energy is convex with respect to the geodesics in this space. So they only have geodesics of regularity C11. So it's a geodesics in the space of potentials. But using the convexity, they're able to show that so these two metrics are connected by a geodesic, and the extremal metrics give a or I guess to be precise, constant scalar curvature metrics give a minimum of the K energy, and if you have a geodesic connecting the two metrics and they're a minimum by convexity, it's minimized along the geodesic, and then you show that the geodesic is induced by a holomorphic vector field. So they are canonical metrics when they exist, but it's still an open problem when they exist. So I'm going to move to the symplectic picture now. So this is used used less, but you can fix a symplectic form and then consider all the compatible almost complex structures. And so I'll write yeah, so I'll use this notation for all for the space of compatible almost complex structures. And so they have to be the vanishing there. Yeah, okay. So they have to be you consider the space of almost complex structures which are compatible with the symplectic form. And so I mentioned last week that these always exist. Just using bundle techniques, that the unitary group is the maximal compact subgroup of the symplectic group. And plus you require that that the associated metric is positive definite. So if it's compatible, then you have an associated metric. So it requires these two conditions. And then you have the subset, which I use the superscript I of integrable almost complex structures. So that's just, in other words, the Nienhaus tensor vanishes. And so then these are, this is the space of Kähler metrics compatible with the symplectic form. And so we'll see that this space is the space of compatible almost complex structures is a smooth Frechet manifold with a Kähler structure. And then this subset of integrable ones is a zero set of the Nienhaus tensor. So this could be a singular subvariety in general. So this is an infinite dimensional Kähler manifold, and the tangent space consists of all tensors which anti-commute with the almost complex structure and satisfy this relation with the symplectic form. So if you rewrite this in terms of the metric, it's the tangent vector is symmetric with respect to the Riemannian metric given by J. So this is in terms of a symplectic form. And so then you can define a complex structure on this manifold. So this is a the infinite dimensional, like Frechet manifold, because I'm considering smooth sections. I guess you could consider like a Banach manifold of certain regularity, but if you consider smooth, almost complex structures, then it's a Frechet manifold. And so then you can define an almost complex structure on it by composing each tangent vector in the tangent space by the almost complex structure there. Yeah, I guess that's annoying. And so to see that it's a genuine infinite dimensional complex manifold, you need charts. And so pick a point in there. So pick an almost complex structure, and then you take a subset of, so essentially you take a subset of the tangent space at this almost complex structure. So the first two conditions mean that mu is in the tangent space, so it anti-commutes with J0, and it's symmetric with the associated metric. But you also require that it satisfies this condition. And so this is similar to I guess what that means. This is similar to the parametrization of complex structures used by Kuranishi in his papers on the deformation, versal deformation space of complex structures. And so then you can define the chart so you can define the chart by what this is the so this is a Kähler transform here, and so it's related to at an almost complex structure, J0, the tangent vectors on the manifold split into types. Oops, sorry. in the 1, 0 and 0, 1 types. And then an almost complex structure, so it can be an almost complex structure can be given by the tensor or the subspace of vectors of, say, type 0, 1. So you could define an almost complex structure as a subspace of the complexified tangent bundle of the manifold, so that it's completely non-real, so its intersection with its conjugate is empty. And so it gives a decomposition of the complexified tangent bundle. And so then this mu, so if you, so this defines an almost complex structure, and if the almost complex structure is close enough to the original one, then this is given by a tensor mu. So this denotes the fixed almost complex structure giving the type decomposition. So the almost complex structure given here, which I guess you could call it J, is given by this tensor where the type decomposition of J in 0, 1 is given by the set of so it's given by the graph of this tensor. So this is like in the work of Kuranishi. And so you need to pair, when he defines the, like he proves that there's a versal deformation space of complex structures, basically does work into Dirac-Spencer theory using this parametrization. So this gives a parametrization, and the reason I'm discussing this is that the this is a Cayley transform related to this picture. So you can consider like the subspace parametrization of almost complex structures. So here you're parametrizing it by by these tensors, which there's an added assumption in our case because we want them to be compatible with the symplectic form. So we require these two more conditions, that mu is symmetric with respect to the metric. And then this third condition requires that the third condition means that the associated metric with respect to the almost complex structure from mu is positive definite. And so then this transform is how you get the almost complex structure tensor J from this subspace. So it's kind of just like fancy linear algebra. So there's two pictures here. There's the, in terms of, well, I'm sorry, I guess there's like one picture in how they're parametrized. The coordinate chart here, which is onto this entire manifold, is given by all of these tensors mu that satisfy these three conditions. You can just think of it in terms of these subspaces, the graphs of mu, or using the Kähler transform that gives you the this is the almost complex structure in this formula here. So in general, if you're not considering a symplectic structure, this is a little bit more complicated because then this chart isn't onto. In this case, it's onto, so this one chart covers the whole manifold here. If you're considering like arbitrary complex, almost complex or complex structures like Kuranishi, then this won't be onto. You have to choose it. Mu has to be close enough to I guess mu can't have an eigenvalue +1 or -1, which that it's automatic in this case that it can't because of condition 3. So I guess so it turns out that this so this proves that it's a complex analytic manifold, but it's also a Kähler manifold. And so A and B are tangent vectors. So those are tensors. So it affects almost complex structure. They're tensors. And so you get a metric by taking the multiplication and the trace. And then there's a Kähler form associated to it. And then you can prove that the Kähler form is closed. And so it's actually even more, it's like formally a symmetric. This is formally a symmetric metric. So if you, so you can work out the Levi-Civita connection and the curvature. It's actually not that hard. And you basically get the curvature has the same formula as a symmetric space. And so the reason I'm doing that is that due to the reason why we're doing this whole space is that, so for one thing, this will kind of include all of these, this space of metrics in the fixed Kähler class. So in this case, we're also fixing the Kähler class, but we're changing the almost complex structure arbitrarily. So the Kähler class of metrics will be contained in here in this picture, but also more. So due to, well, I guess first, the symplectomorphism group. So the symplectic manifold, compact symplectic manifold. So it acts by, so you can check from the formulas that it acts by holomorphic isometries on this Kähler manifold, infinite dimensional Kähler manifold. And so this will also have the subgroup of Hamiltonian automorphisms. Yeah, let's see how much time we have. So it's a connected. So these are finite dimensional. Or sorry, no. Why did I say that? These are infinite dimensional groups. And so this will be so a Hamiltonian the Hamiltonian group so assume you know what a Hamiltonian vector field is. So symplectic automorphism group is Hamiltonian if there is an isotopy, so a path of symplectomorphisms connecting it to the identity. So at t equals 0, it's the identity. C1 is C. So that it generates, so that the path is this path is generated by Hamiltonian vector fields. So so if you, this path will be generated by vector fields, and it's a Hamiltonian isotopy if these vector fields have Hamiltonian functions that vary smoothly with t. So then this is a so this is a subgroup. So you can show that they're both infinite dimensional Lie groups. So in this situation, so every vector field is Hamiltonian if the first de Rham cohomology is 0. So here, this is is equality if the first de Rham cohomology is 0. But if the H1 first de Rham cohomology is not 0, then this will be a proper subgroup. Okay, so if you consider, I use different notation here. If you consider the subgroup of Hamiltonian automorphisms of the manifold, so the symplectic group gives holomorphic isometries of the space of almost complex structures. But if you consider the subgroup of Hamiltonian isometries, then you can show that so this is the result of, I guess this should be Fujiki misspelled. Result of Fujiki and Donaldson, that the scalar curvature is a moment map for this action. So this doesn't extend to the larger symplectic group, so you need to restrict to the Hamiltonian transformations. So the scalar curvature is a moment map, and this is one way to explain some of the problems in Kähler geometry in terms of stability, because there's the Kemp-Ness theorem involving moment maps. And so last time I mentioned the Yau-Tian-Donaldson conjecture, that the existence of a constant scalar curvature metric is conjectured to be equivalent to geometric stability of the polarized complex manifold underlying things. And so the Kemp-Ness theorem says that an orbit of J should have a 0 of the moment map if and only if it's a stable orbit in the finite dimensional Kemp-Ness theorem. And so this infinite dimensional problem is analogous, but it's just unsolved because it's there's no the Kemp-Ness theorem is a result in finite dimensional GIT. So if J is not integrable, then it's not the order. Then the scalar curvature here for non-integrable almost complex structures is not the Riemannian scalar curvature. It's a Hermitian scalar curvature. So maybe I can say something about that. Yeah, so this result of Fujiki and Donaldson doesn't require J to be integrable, but you use the scalar curvature of a Chern connection. And so in general, in that situation, if J is not integrable, this is a almost Kähler structure. And then J is not parallel with respect to the Levi-Civita connection, but it is with respect to so if nabla is a Levi-Civita connection, then the Chern connection is this object. So this formula is just projecting the Levi-Civita connection onto the connection which preserves J. And so you take the curvature of this and the trace on the first two entries of the curvature and the last two entries, and it gives you a scalar curvature. Which is what's used as the moment map in that case. So here we have the action of the Hamiltonian group, and in analogy with finite dimensional geometric invariant theory, I guess so in the notes here in the slides, I've denoted script G as the Hamiltonian group. And you'd like to consider, if you're going to kind of work as in the finite dimensional geometric invariant theory, you consider the orbits of the complexified group. So this is analogy with the analogy of this group. So this is infinite dimensional. The finite dimensional analogy would be a compact Lie group. So it's obviously not because we're in infinite dimensions, but then the complexified group would be a reductive group. But the problem in this case is that this is not an actual group. There's no complexification of the Hamiltonian group. But you can complexify the Lie algebras. So the Lie algebra of the Hamiltonian group. So you can consider all Hamiltonian vector fields, but using some symplectic geometry, you can consider all of the all smooth functions. So every smooth function, so these are just normalized, the zero means. Every smooth function has a corresponding Hamiltonian vector field. And so they give the Lie algebra, the smooth functions give the Lie algebra of the Hamiltonian group. And so if you're considering functions, then it's the bracket is the Poisson bracket. So I should explain what more about the moment map. So if you have a Hamiltonian, so you have a function, then it has the corresponding Hamiltonian vector field, so defined by this relation. And so then the Hamiltonian group has the infinitesimal action on this manifold given by, we'll call the action by capital P. So this defines a vector field on this manifold of almost complex structures. But so at each point at J, it's given by the Lie derivative action. And so the assertion is that the scalar curvature is the moment map. So we write the infinitesimal action of the scalar curvature is Q. And so being a moment map means that that if you act by the so the moment map evaluated on a Hamiltonian function. So I'll take the normalized scalar curvature, the Hamiltonian function. So this is the moment map evaluated on this element of the Lie algebra. And then this being a moment map means that if you act by, so I'll say like act by alpha is a tangent vector, then acting on here. So this just acts on the part that depends on J, which is the scalar curvature. So then this is equal to the moment map evaluated on this element of the Lie algebra is given by the corresponding vector on the manifold evaluated with the tangent vector. And then it's also to be a moment map, it's also equivariant. So this is what was proved by Fujiki, and then later by Donaldson. Without Donaldson proved it for just general almost complex structures. So how does this is related to what we've covered so far? So if you're given, so I've mentioned that the Hamiltonian group so it doesn't have a complexification, but we can still consider the complexified orbit. So so fix a so fix an integrable complex structure. Otherwise, this doesn't really work. And then consider so this is a Kähler structure. So then consider all almost complex structures so that there exists a diffeomorphism, so it's isotopic to the identity with J is the image of J0. So in general, these aren't going to be, if you take an arbitrary diffeomorphism, this isn't going to be in here. It's not going to be compatible with omega. But if you just consider those that are, then this gives you, I guess, what you can consider an orbit in here. And so then this is essentially all of these almost complex structures are the space of these almost complex structures. So you consider just the connected piece here that you can get like this. And if you quotient out by the symplectomorphism group, then this space is the space of Kähler metrics in the given Kähler class with your complex structure J0, but I guess actually though quotiented by the holomorphic automorphism group. So I guess it's not quite the same thing, but this orbit here is like up to the symplectomorphisms is the Kähler class. So in a lot of the work, I think there's other work of Donaldson where he works on this orbit to try to prove the existence of like special Kähler metrics, like balanced metrics. So then you can consider this to be you can consider this to be this collection of metrics to be the orbit of the complexified Hamiltonian group, which doesn't exist. So this group doesn't exist, but you have this orbit. And so then this is actually not that hard to prove. So this follows from Moser's argument. So a diffeomorphism will take this to a compatible vector field if it pulls back omega to a type 1,1 Kähler metric. So so if it pulls this back to a Kähler metric, this will happen if the symplectic form pulls back to a Kähler metric with respect to J0. But the space of almost complex structures is larger, so it contains this orbit, which is basically the Kähler class. So you can also consider this infinitesimally. So if you consider the action, so the smooth functions are the Lie algebra, the Hamiltonian group. If you complexify that, then you kind of get the complexification of the Lie algebra, the Hamiltonian group. And so then you could say that two complex structures are in the same orbit of the complexified group, which again doesn't exist. If there's a path of almost complex structures whose derivative is tangent to the action of the Hamiltonian group. Okay, so yeah, so I guess this is just a restatement here, what I wrote, that a diffeomorphism will take one complex structure to another. So J1 will be compatible with the symplectic form if and only if the symplectic form pulls back to a Kähler metric. So the paper that I'm writing, I'm considering deforming constant scalar curvature and extremal metrics. So we're starting with a integrable almost complex structure. So the structure is a Kähler structure we're starting with. And so first we construct a deformation space like Kuranishi did in the 60s, getting the deformation space of complex structures. But here we want to consider them that are complex structures which are compatible with the symplectic structure. So so we restrict to the complex structures in this space, and they'll be modulo not the full diffeomorphism group, but say the complexified Hamiltonian group, which because again we could describe what these orbits are, but this isn't an actual group. So, but we have the infinitesimal action, and then so the infinitesimal action will go from the Lie algebra to the tangent space. But then if you also consider the D bar, so So if you consider the tangent vectors as so I guess we shouldn't be the I here because we're considering tangent vectors. But these will consist of all, in complex notation, it'll be um, 0, 1 forms with values in 1, 0, but they must be symmetric. So that means that if you lower this index here, then it's the symmetric product of this with itself. So this is contained in the tensor product. So if you use the metric to lower the tangent vector component to a 0, 1 form component, so then you take the subspace of these, which are symmetric subspace of the tensor product. And so then you have the del bar acting on this. But again, we take the kernel of so we're taking a subspace of the complex that's taken in with the Kuranishi deformation theory, because we're considering almost complex structures compatible with the symplectic form. So so what you do is you take, so we're taking the Dolbeault complex with values in the holomorphic tangent bundle, but we're taking a subspace of that. So to get the subspace, you take you lower the tangent vectors to the forms of type 0, 1, and then you wedge here. I guess this should be like the 0, 3, not 3. So you wedge, and then you take the kernel of this mapping. This will give you the degree 2 component of the complex. So so we get this complex. So you take all the sections of the kernel here, I call that B. And so then this gives us the complex. And then the first cohomology of this is like the kernel of del bar here, and then the kernel of the adjoint. This is the Lichnerowicz operator. So this is the second order operator P. So the paper I'm working on, I work out the Kuranishi theory in this context, which is kind of follows the same pattern as Kuranishi's papers, but with other difficulties. So the problem I've worked on is deforming a constant scalar curvature Kähler or extremal Kähler metric. So start with so here I'll just for simplicity, consider the constant scalar curvature Kähler case. So take a constant scalar curvature Kähler element here, so the complex structure, and suppose that the so I guess I forgot to say here that that the automorphism group of or isometry group is a Lie group K. So this is a compact Lie group. So I guess the isometry group, in other words. Then we can prove that there's a ball in the harmonic space of the deformation complex and a K equivariant map such that the orbit of this orbit of the complexified Hamiltonian group of every nearby integrable almost complex structure intersects this slice. And if 2 points are in the same, so then you also have the complexification of the isometry group acts on the harmonic space here. So it acts on the ball. And so first you construct the Kuranishi slice, but then we also perturb it so that the moment map, which is the scalar curvature, restricted to this slice, so we can perturb this slice so that the moment map has values in the Lie algebra of the isometry group of J0 of the center point. So just restricted to this slice, you have the moment map has values in the Lie algebra of the isometry group of J. So this is first you have to, so there's 2 steps to this. First you have to construct the Kuranishi space, and then you have to perturb it to get a finite dimensional moment map. So this is actually an old argument that goes back to other papers, but interestingly though, every time I find this done, there's holes in the papers, as I'll explain later. I guess it's kind of cut off here. So first you use the Kuranishi theory to get a K equivariant slice here. And then you need to perturb it to cancel out. So the moment map has values in the Lie algebra of the Hamiltonian group, which is all smooth functions. I guess here normalized at integral 0. But you can perturb this slice to cancel out the portion perpendicular to the isometry group of J0. So yeah, I guess this didn't turn out right here. So all of the smooth functions, so the Lie algebra, the Hamiltonian group splits into the Lie algebra of just using the L2 inner product, splits into the Lie algebra of the isometry group of J0 and its orthogonal complement. And so a implicit function theorem argument you can use to cancel out K perp here. And this is where I've there's been maybe 5 or 10 papers using this argument somewhere, and there's always a hole in them. And I think it's because they always want to use the Banach implicit function theorem, and it doesn't work here. Because that is typical of a lot of deformation problems. You have to use the more sophisticated Nash-Moser theorem. The Banach theory has problems. Okay, so consider it. So I'll describe the argument. Consider a neighborhood of 0 in the space of smooth functions. And then so consider the path of Kähler metrics using from omega to omega plus d bar phi, sort of the path, and then so this is like Moser's argument, and then get the t-varying vector field as follows. And then by integrating the t-varying vector field, you get a diffeomorphism, which takes omega 1 back to omega. And then that gives you a, this was implicit in some of the other things I did, but I didn't go over the details. But then this gives you the new almost complex structure, or complex structure, which is compatible with omega. Because it takes this Kähler structure back to this one. So this is the Kähler isometry here with this almost complex structure with the original omega. And then this, so there's you differentiate phi twice here, and then when you act on J, you differentiate again. So it takes, if it's K differentiable phi, it takes it to K minus 3 differentiable J here. So this gives you a map. So I take the projection onto the orthogonal part of the Lie algebra, the Hamiltonian group, perpendicular to K. That's what pi is here, and this is the scalar curvature. That's in the Lie algebra, the Hamiltonian group. So you get this map, and then you can check that its derivative with respect to phi. So V is the neighborhood in the perpendicular space here. You can check that the derivative of this with respect to phi is a elliptic operator, which is an isomorphism at the origin, because it's just the Lick-Arabix operator and then composed with its adjoint. So this is elliptic fourth order operator. But this is where like the papers where this is done on the in the literature, at least all that I've found, like have missed this, that the derivative is a fourth order elliptic operator, but this is a fifth order nonlinear map here. So the Banach implicit function theorem doesn't apply. But it's been known for a while, like that the Nash-Moser theorem can fix this. So if you try to use like Banach spaces here, like the not Holder spaces, but Sobolev space here, then this mapping, this is a nonlinear map, which is elliptic in phi, if you differentiate it here. But you lose it. This is a fifth order nonlinear map with a fourth order derivative. So then the elliptic, so then the Banach, the elementary Banach implicit function theorem doesn't work. But this is a common use, I think, of the Nash-Moser theorem is in deformation problems, because sometimes you differentiate something and you get an elliptic operator as the derivative, but it doesn't have as many, but the elliptic operator is a lower order than your original function. And so I think that's a situation where the Nash-Moser theorem is useful, has applications. So I guess it obviously goes back to John Nash in his embedding theorem, like in the 50s, but the readable source is this long paper by Richard Hamilton. And so I guess don't only have a few more minutes. It's the theorem is a long story, but this is a long paper, so it kind of explains everything. In the Nash-Moser theorem, you consider Fréchet spaces. So those are a topological vector space with a countable number of complete topological vector space that's given by a countable number of semi-norms. And so the typical ones are smooth sections of vector bundles. And so then for the Nash-Moser theorem, you require the Fréchet spaces and maps to be tame. And so this involves bounds on, this involves kind of a grading of norms and bounding the norms even on nonlinear functions. So in this case, you just show that it's these are Taine spaces and G is a Taine map. And you also have to show that the derivative is invertible in a neighborhood of the origin, not just at the origin. But this can be done because this is an elliptic operator that's invertible at the origin. So X would be J0 and phi would be 0. And so it's an elliptic operator, I guess, restricted away from the kernel. So restricted in the perpendicular. But if you have an invertible elliptic operator and you perturb its symbol, then it's still an invertible operator. So then this will be invertible in a neighborhood. So that gives the, so with the right implicit function theorem, here you can perturb to cancel out the perpendicular part of the perpendicular part of the moment map. So you're just left with the finite dimensional you're just left with this slice. The scalar curvature restricts to a finite dimensional moment map into the Lie algebra of the automorphism group of the central. And so then this can be used to consider the deformation problem. And so I guess, unfortunately, it's already 6. So the next part of the argument is you have a finite dimensional moment map on this slice. And then one can prove that a finite dimensional can't nest in this situation where if you have a point in the slice, so it's a bit complicated because the perturbation we just did is not holomorphic. So the complexified orbits here you consider them on the harmonic space. They don't quite correspond to the slice. But nevertheless, you can still prove that if you have a point, so this, you have the linear action of this complexified group. If the orbit is locally closed, the complexified orbit is locally closed, that means that the point is polystable. Then you can show that the moment map that we have restricted has a 0. So that's a constant scalar curvature structure. So there's more to the argument because there's some technical problems mentioned, but it's done by, so consider the action of the automorphism group of the center of the slice J0, so that's K. Then you can consider the flat moment map. So consider the like flat Hermitian structure given by at the center of the slice. And then the moment map of that linear structure. And then by considering the Taylor series, so this is the genuine moment map we're interested in, the restriction of the scalar curvature. So to take the Taylor series, then mu 0 is 0 here because it's a constant scalar curvature metric. D mu is 0 because the K preserves the central complex structure J0. And then you have this derivative at t equals 0. And then you can check that this term gives the flat moment map nu. So we get this approximating equation. So up to third order in the radial direction. So then it's an easy exercise that the flat moment map nu is given by this formula. Where this is the restriction of the Kähler form on the space of almost complex structures just to the center point of at J0. So this is because our perturbed slice isn't holomorphic, there's we only have an approximation here, but it's close enough to prove yeah, so I don't know if there are any more questions. If there's any questions, because I guess I'm already over time. So,
Okay, any questions from the audience?
yeah, there's probably not any point to trying to go through the details of this because we're out of time.
All right, yeah, thank you very much. If you would like to give another talk, we can consider.
It works for extremal structures also because if you take the so this finite dimensional argument works if you're familiar with the moment map, if you take the norm squared, so if you have a finite dimensional moment map, if you take its norm squared, then its critical points will be points where so critical points of this where its gradient is 0 will be points where the moment map is in the stabilizer of that point. So in the finite, in this, once you reduce to the finite dimensional picture, you can also look for, so if you're starting with an extremal structure, you can work by looking for critical points of the norm squared of the moment map. So then this is also the Calabi functional. But I'll stop here.
All right. Thank you very much.